Have you ever gazed up at the night sky and pondered the hidden stories written in the rings of Saturn or the enigmatic faces of its moons? Beyond its breathtaking beauty, Saturn is a celestial body shrouded in mystery, a cosmic puzzle that has baffled scientists for decades. From its dazzling rings to its strange companions orbiting silently in the darkness, this planet holds secrets that challenge our understanding of the universe. But what if we told you that within these mysteries lies knowledge that could redefine everything we know about planetary science and perhaps even life itself? In this video, we're diving deep into 25 unexplained mysteries of Saturn, each one more intriguing than the last. Stay with us as we uncover clues, question theories, and marvel at the wonders of this distant world. The journey begins now. Let's start our journey into Saturn's mysteries with one of the most visually stunning and scientifically perplexing phenomena, the hexagon at its north pole. Imagine a massive, six-sided jet stream encircling the planet's polar region, stretching thousands of miles across and remaining eerily stable for decades. This structure was first glimpsed by the Voyager spacecraft in the early 1980s and later studied in greater detail by the Cassini mission, revealing its intricate patterns and persistent nature. What makes this hexagon so extraordinary is not just its geometric precision but also its longevity. Unlike Earth's weather systems, which are constantly changing due to atmospheric dynamics, Saturn's hexagon has remained largely unchanged since its discovery. Scientists believe it may be linked to the planet's deep atmospheric layers, where winds flow in organized patterns that create such long-lasting features. However, the exact mechanisms behind its formation and stability remain unclear. There are several theories attempting to explain how this six-sided marvel came to be. One popular hypothesis involves standing wave patterns within Saturn's atmosphere. These waves could interact with the planet's rotation and wind speeds, producing the distinct hexagonal shape we observe. Another idea suggests that fluid dynamics on a planetary scale might naturally produce such structures under certain conditions. Yet, despite these insights, no model has fully replicated the hexagon's unique properties in laboratory settings or simulations. Adding to the intrigue is the fact that nothing like this exists anywhere else in our solar system. While other planets exhibit complex atmospheric behaviors, none have produced anything as structured or enduring as Saturn's hexagon. Its existence challenges our understanding of planetary atmospheres and raises questions about whether similar phenomena might occur elsewhere in the universe. As we delve deeper into this mystery, it becomes clear that the hexagon represents more than just an oddity. It offers clues about Saturn's internal workings and atmospheric processes. By studying this enigmatic feature, scientists hope to uncover fundamental principles governing gas giants and perhaps even refine models of climate and weather across different worlds. And while we may not yet have all the answers, the hexagon continues to inspire awe and curiosity, reminding us that there is still much to learn from this distant giant. Next, let's turn our attention to another fascinating aspect of Saturn: its iconic rings, which hold their own set of unsolved puzzles waiting to be unraveled. Shifting our focus deeper into the science behind Saturn's enigmatic hexagon, let's explore some of the leading hypotheses that attempt to unravel its origins. Scientists have proposed various theories involving atmospheric waves, standing wave patterns, and fluid dynamics, each offering unique insights into this extraordinary phenomenon. However, as fascinating as these ideas are, they still leave many questions unanswered, particularly regarding the hexagon's energy source and its remarkable persistence over decades. One prominent theory suggests that the hexagon arises from standing wave patterns within Saturn's atmosphere. These waves occur when disturbances in the air, such as wind currents or temperature gradients, interact with the planet's rotation. On Earth, similar processes generate weather systems like hurricanes or jet streams, but none exhibit the geometric precision seen on Saturn. Researchers believe that the combination of Saturn's rapid spin and its deep atmospheric layers creates conditions ripe for producing stable, organized shapes like the hexagon. Yet, while laboratory experiments and computer models have successfully recreated wave-like structures, none have precisely matched the size, symmetry, or longevity of Saturn's feature. Another intriguing possibility involves fluid dynamics at a planetary scale. Imagine the gases swirling around Saturn as a vast ocean of moving particles governed by complex physical laws. Under certain conditions, such systems can naturally form polygonal shapes due to interactions between pressure zones, wind shear, and rotational forces. This concept has been tested through simulations where researchers adjusted variables like viscosity, density, and velocity to replicate the hexagon's appearance. While promising, these efforts often fall short in explaining why the structure remains so unwavering despite being exposed to constant environmental changes. Perhaps one of the most puzzling aspects of the hexagon is its energy source. Unlike Earth, where sunlight drives atmospheric activity, Saturn receives far less solar radiation, especially near its poles. So what powers this colossal storm? Some speculate that internal heat from the planet's core might play a role, providing the necessary energy to sustain the hexagon's motion. Others propose that the interaction between Saturn's magnetic field and charged particles in its atmosphere could contribute to the system's stability. Despite these theories, pinpointing the exact mechanism remains elusive, leaving scientists searching for clues buried deep within the planet's turbulent skies. Adding to the complexity is the question of how the hexagon manages to persist without significant alteration over time. Weather patterns on Earth typically evolve rapidly due to factors like changing seasons, landmasses influencing airflow, and varying levels of solar heating. By contrast, Saturn's hexagon defies such expectations, remaining steadfast even as other features in its vicinity come and go. Could it be tied to the planet's unique composition, perhaps influenced by compounds in its atmosphere not yet fully understood? Or does it represent a fundamental principle of fluid mechanics that we have yet to discover? As we continue to probe the mysteries of Saturn's hexagon, it becomes increasingly clear that understanding this phenomenon will require advancements across multiple fields of study. From refining computational models to developing new observational techniques, each step brings us closer to unlocking the secrets hidden within this celestial marvel. And though the answers may remain just out of reach for now, the pursuit itself enriches our knowledge of planetary science, reminding us once again of the wonders waiting to be explored among the stars. With this in mind, let's now shift our gaze toward another captivating mystery: Saturn's majestic rings, which hold their own set of unsolved riddles. Moving on from the enigmatic hexagon at Saturn's North Pole, let's turn our attention to another breathtaking feature of this gas giant: its stunning rings. Saturn's rings are among the most iconic structures in our solar system, captivating astronomers and space enthusiasts alike for centuries. But despite their beauty, these rings remain shrouded in mystery, with many fundamental questions about their composition, structure, and age still unanswered. Saturn's rings are primarily composed of ice particles, ranging in size from microscopic dust grains to massive chunks as large as boulders. Mixed within this icy material are traces of rock and other compounds, giving the rings a faintly reflective appearance when observed through telescopes. This mixture of water ice and rocky debris creates an intricate tapestry of brightness variations across the ring system, making each section unique. However, the exact proportions of these components and how they came together to form such a spectacular structure remain unclear. Structurally, Saturn's rings consist of thousands of individual ringlets separated by gaps and divisions. The main sections, labeled A, B, and C, vary significantly in thickness and density, For example, the B ring is the thickest and brightest, while the O ring contains features like the Encke gap and the Keeler gap, both sculpted by nearby moons. Meanwhile, the C ring, also known as the Crepe ring, appears dimmer due to its lower particle concentration. These structural differences hint at complex interactions between gravitational forces, orbital dynamics, and collisions occurring within the rings themselves. One of the most intriguing aspects of Saturn's rings is their apparent youth compared to the planet itself. Current estimates suggest that the rings may be only a few 100 million years old, a mere blink of an eye in cosmic terms relative to Saturn's estimated age of over 4 billion years. How could something so grand and central to Saturn's identity have formed relatively recently? Some scientists propose that the rings originated from the destruction of a moon or comet that ventured too close to Saturn, torn apart by tidal forces into the debris now forming the rings. Others speculate that ongoing processes, such as meteorite impacts or gravitational perturbations, continuously replenish the rings with fresh material, keeping them looking younger than expected. Adding to the puzzle is the observation that certain parts of the rings appear even younger than others. Studies conducted during the Cassini mission revealed localized regions where the ice particles seem pristine, untouched by radiation or micrometeoroid bombardment. Why do these areas remain so unblemished while surrounding sections show signs of aging? Could it be evidence of recent events reshaping specific portions of the rings, or does it point to underlying mechanisms maintaining distinct zones within the overall structure? Furthermore, the rings' evolution remains poorly understood. Are they slowly dissipating over time, destined to vanish entirely millions of years from now? Or will they persist indefinitely, shaped by dynamic processes yet to be fully uncovered? These questions challenge researchers to delve deeper into the physics governing planetary rings and consider whether similar phenomena occur elsewhere in the universe. In summary, Saturn's rings offer a mesmerizing window into the complexities of celestial mechanics, presenting us with countless riddles waiting to be solved. As we continue to explore these remarkable formations, each discovery brings us closer to understanding not just Saturn, but also the broader principles shaping our solar system. With new missions planned and advanced technology on the horizon, the secrets of Saturn's rings may soon come to light, revealing even more wonders hidden within this distant world. Shifting our focus from the mesmerizing rings, let's dive into another fascinating mystery surrounding Saturn, its unexpected internal heat production. Unlike Earth, which generates heat primarily through radioactive decay, Saturn emits significantly more energy than it receives from the Sun. This surplus heat poses a puzzling question. How does a planet over 4 billion years old still generate such an extraordinary amount of warmth? Saturn's internal heat is nearly 5 times greater than what scientists would predict based on its age and composition. For comparison, Jupiter also radiates excess heat, but not to the same degree as Saturn. So, what could be driving this phenomenon? Several theories have been proposed, each offering intriguing possibilities while leaving many questions unanswered. One leading hypothesis involves a process known as helium rain. In this scenario, helium droplets form deep within Saturn's dense atmosphere due to differences in density between helium and hydrogen. As these droplets sink toward the planet's core, they release gravitational potential energy, contributing to the observed heat output. While this explanation aligns well with some observations, challenges remain in fully validating the theory. For instance, the exact distribution and behavior of helium inside Saturn are still uncertain, making it difficult to confirm whether helium rain alone accounts for all the extra heat. Another possibility lies in gravitational contraction, where Saturn continues to shrink slowly over time. This gradual compression generates heat as the planet's interior adjusts to its decreasing size. However, given Saturn's immense age, one might expect this process to have tapered off long ago. yet the evidence suggests otherwise, indicating that something unusual is happening beneath the surface. A third idea combines both mechanisms, proposing that helium rain enhances the efficiency of gravitational contraction by altering the thermal structure of Saturn's interior. This hybrid approach offers a compelling way to reconcile various observations, though it requires further investigation to determine its validity. Despite these hypotheses, definitive answers remain elusive. Observations from missions like Cassini provide valuable data, yet they fall short of painting a complete picture. Scientists continue to refine models and conduct experiments in laboratories simulating extreme pressures and temperatures akin to those found within Saturn. These efforts aim to unlock the secrets behind its mysterious heat production. The implications of solving this puzzle extend beyond Saturn itself. Understanding the processes at work within gas giants helps illuminate broader principles governing planetary formation and evolution. Moreover, studying Saturn's heat dynamics may offer insights into other planets exhibiting similar behaviors, potentially even exoplanets far beyond our solar system. In summary, Saturn's missing heat problem remains one of the most intriguing mysteries about this distant world. Whether driven by helium rain, gravitational contraction, or some combination of forces yet to be discovered, the truth awaits further exploration. By unraveling this enigma, we edge closer to comprehending not just Saturn, but also the fundamental workings of gas giants throughout the cosmos. Transitioning from Saturn's puzzling internal heat, let's journey outward to explore another extraordinary aspect of the Saturnian system, Titan, a moon so remarkable that it defies conventional expectations of what a celestial body can be. Among all the moons in our solar system, Titan stands out for its incredibly thick atmosphere, which is even denser than Earth's. This unique feature sets Titan apart as one of the most intriguing objects in the cosmos. What makes Titan's atmosphere particularly fascinating is its composition. Nitrogen dominates this envelope of gases, much like on Earth, but here the similarities end. Unlike Earth, Titan's atmosphere contains a rich cocktail of organic compounds, including methane and ethane. These hydrocarbons play a crucial role in shaping Titan's environment, contributing to a weather cycle that mirrors processes seen on our own planet, but with a twist. Instead of water, liquid methane forms clouds, falls as rain, and collects in vast lakes and rivers across Titan's surface. This methane-based hydrological cycle creates a landscape eerily reminiscent of Earth, albeit under vastly different conditions. Titan boasts large bodies of liquid methane and ethane, such as Kraken Mare, the largest known sea on the Moon. Alongside these seas, intricate networks of river channels carve through Titan's terrain, transporting liquid methane over distances comparable to those of terrestrial rivers. Such features make Titan one of the few places in the solar system where liquid exists on the surface, albeit in a form quite alien to us. Beyond its surface features, Titan's atmosphere harbors a wealth of complex chemistry. Ultraviolet radiation from the Sun triggers reactions high above the Moon's surface, producing an array of organic molecules. Some scientists speculate that these reactions might resemble the probiotic chemistry thought to have occurred on early Earth, raising tantalizing questions about the potential for life, or at least life-like processes, to arise in environments far removed from ours. Moreover, Titan's dense atmosphere shields its surface from harsh cosmic rays and meteorite impacts, creating a relatively stable environment beneath. This protection fosters conditions somewhat analogous to those found on Earth billions of years ago, offering a natural laboratory for studying how life might emerge in extreme settings. While no definitive evidence of life has been discovered, the presence of such Earth-like processes deepens the intrigue surrounding Titan. Another striking parallel between Titan and Earth lies in their respective atmospheres' ability to support dynamic weather systems. Storms of methane occasionally erupt across Titan's surface, bringing dramatic changes to its landscape. observations by the Cassini spacecraft revealed evidence of seasonal variations, suggesting that Titan experiences climatic shifts similar to those driving Earth's weather patterns. However, due to Saturn's longer orbital period around the Sun, these seasons last for decades rather than months or years. In summary, Titan's thick nitrogen-rich atmosphere, combined with its methane lakes, rivers, and organic chemistry, paints a picture of a world both familiar and utterly foreign. Its resemblance to Earth, despite operating under entirely different physical principles, challenges our understanding of planetary science and broadens the scope of possibilities for habitability in the universe. By examining Titan, we gain invaluable insights into the diverse ways planets and moons can evolve, reminding us just how much there is still to learn about the wonders hidden within our solar system. Shifting our gaze from Titan's enigmatic atmosphere, let's dive deeper into another captivating mystery of the Saturnian system, Enceladus, a small yet extraordinary moon that has captured the attention of scientists worldwide. Enceladus is best known for its dramatic water vapor plumes, which erupt spectacularly from fractures near its south pole. These geysers are not just a stunning sight, they provide crucial clues about the moon's subsurface ocean and its potential to harbor life. The discovery of these plumes was first made by NASA's Cassini spacecraft in 2005. Observations revealed that the jets consist primarily of water vapor, along with traces of nitrogen, ammonia, methane, and other organic compounds. These chemicals suggest complex chemical processes occurring beneath the icy crust, possibly driven by hydrothermal activity. Scientists believe the source of these geysers lies in an extensive subsurface ocean, sandwiched between layers of ice deep within Enceladus. What makes Enceladus particularly intriguing is the possibility that this hidden ocean could be habitable. The presence of salts and silica particles in the plumes indicates conditions similar to those found around hydrothermal vents on Earth, a known haven for microbial life. Additionally, the detection of molecular hydrogen in the plumes points toward ongoing geological activity, potentially providing energy sources necessary for life. This combination of liquid water, organic molecules, and available energy makes Enceladus one of the most promising candidates for extraterrestrial life in our solar system. But how exactly do these geysers form? Researchers hypothesize that tidal forces exerted by Saturn cause stress on Enceladus' icy shell, creating fissures called tiger stripes. Through these cracks, pressurized water from the subsurface ocean escapes into space, forming the towering plumes we observe. The process is akin to a natural geyser here on Earth, though operating under vastly different temperatures and pressures. Ongoing research continues to unravel the mysteries surrounding Enceladus geysers and their implications for habitability. Future missions aim to collect more detailed data, including direct sampling of the plumes, to search for signs of life or prebiotic chemistry. Some proposals even envision sending robotic submarines to explore the ocean itself, should technology allow it in the coming decades. As we peer into the heart of Enceladus, we are reminded once again of the incredible diversity of worlds within our solar system. Each new discovery brings us closer to understanding not only the origins of life, but also the fundamental processes shaping celestial bodies far beyond our own planet. With Enceladus as a tantalizing example, the search for alien life takes on a renewed sense of urgency and excitement, reminding us just how much there is still to learn about the cosmos. From Enceladus' breathtaking geysers, we now turn our attention to another fascinating phenomenon in Saturn's realm, the chaotic rotation of Hyperion, a moon unlike any other in the solar system. Hyperion's chaotic rotation takes us to one of Saturn's most peculiar moons, a cosmic oddity that defies the usual rules of celestial motion. Imagine a moon shaped like a giant sponge, its surface pockmarked with craters and its movement through space utterly unpredictable. This is Hyperion, a small yet fascinating body orbiting Saturn in a way that has puzzled scientists for decades. Unlike most moons, which rotate predictably and maintain a stable orientation as they orbit their parent planet, Hyperion spins wildly, tumbling end over end without any discernible pattern. Its irregular shape plays a significant role in this chaotic behavior. Unlike spherical moons, Hyperion lacks the gravitational forces needed to pull it into a neat, round form. Instead, it resembles a misshapen potato with dimensions that vary significantly along different axes. This asymmetry causes its rotation to become unstable, leading to what scientists call chaotic rotation. But what exactly drives this erratic dance? The answer lies in the delicate interplay between Hyperion's irregular shape and the gravitational influence of Saturn and its neighboring moons. As Hyperion orbits Saturn, it experiences varying tidal forces due to its proximity to larger bodies such as Titan. These forces constantly tug at Hyperion, altering its spin rate and axis of rotation. The result is an unpredictable motion where no two rotations are alike, making long-term predictions nearly impossible. To better understand this phenomenon, researchers have turned to mathematical models and simulations. By using complex equations based on classical mechanics, they attempt to replicate Hyperion's chaotic behavior under various conditions. One key concept employed in these studies is the idea of a strange attractor, a term borrowed from chaos theory. A strange attractor describes systems whose outcomes appear random but are actually governed by underlying deterministic rules. In the case of Hyperion, its chaotic rotation can be thought of as being drawn toward such an attractor, producing seemingly erratic patterns that still adhere to certain physical constraints. These models reveal that even small changes in initial conditions, such as slight variations in Hyperion's shape or position, can lead to dramatically different results over time. This sensitivity to initial conditions underscores the essence of chaos theory and helps explain why predicting Hyperion's future orientation remains so challenging. Yet, despite the complexity involved, these simulations provide valuable insights into the dynamics of non-spherical objects in space, offering lessons applicable beyond just Hyperion itself. So, what does all this mean for our understanding of Saturn's moons? Hyperion serves as a striking example of how diverse and intricate the motions of celestial bodies can be. It challenges traditional notions of stability and order in planetary systems, reminding us that there is much more to explore in the vastness of space. While we may not yet fully comprehend every aspect of Hyperion's chaotic rotation, each new discovery brings us closer to unraveling the mysteries of this remarkable moon and perhaps others like it throughout the universe. As we leave behind Hyperion's unpredictable dance, let's now shift our focus to another intriguing feature of Saturn's system, Iapetus' mysterious equatorial ridge. Iapetus' equatorial ridge presents one of the most striking features in the entire Saturnian system, a colossal mountain range stretching along the moon's equator, creating an appearance akin to a walnut. This ridge, which towers up to 13 kilometers high and spans nearly 2/3 of Iapetus' circumference, has left scientists baffled since its discovery by the Cassini spacecraft. How did such a structure form on a small moon like Iapetus, and why does it align so precisely with the equator? One theory suggests that this ridge may be the remnants of an ancient ring system around Iapetus. Imagine a time when the moon was surrounded by a disk of debris, much like Saturn's famous rings today. Over millions of years, gravitational forces could have caused this material to coalesce and fall onto Iapetus' surface, forming the ridge we see now. However, this explanation raises questions about how such a process would result in such a neatly aligned feature without disrupting the rest of the moon's terrain. Another hypothesis points toward internal processes within Iapetus itself. Some researchers propose that tectonic activity once shaped the moon's surface, pushing material upward along its equator as the body cooled and contracted over billions of years. Yet, Iapetus is far smaller than planets where similar tectonic forces are typically observed, making this scenario less likely unless some unique conditions existed during its early history. A third possibility involves the capture of external debris. Picture Iapetus capturing fragments from collisions between nearby objects or other moons in its orbit. These impacts might have accumulated along the equator due to centrifugal forces acting on the incoming particles, eventually building up into the massive ridge seen today. While intriguing, this idea struggles to explain why the ridge remains so well defined after countless eons of erosion and bombardment. Each of these theories brings us closer to understanding this enigmatic structure, yet none fully answers all the questions surrounding Iapetus' equatorial ridge. What makes this mystery even more compelling is its implications for our broader understanding of planetary formation and evolution. If the ridge formed through interactions with a former ring system, it challenges assumptions about the stability of such structures over cosmic timescales. Alternatively, if tectonics played a role, it suggests that even relatively small bodies can harbor dynamic internal processes under certain circumstances. As scientists continue to study Iapetus and refine their models, they uncover new clues but also encounter fresh puzzles. For instance, recent observations indicate that the ridge isn't uniform throughout. Sections vary in height and composition, hinting at differences in the mechanisms responsible for its creation. Moreover, the alignment of the ridge with Iapetus' equator implies a deep connection to the Moon's rotational dynamics, raising further questions about the interplay between orbital mechanics and surface geology. In summary, Iapetus' equatorial ridge stands as a testament to the complexity and diversity of celestial phenomena. Whether it originated from external debris, internal forces, or something entirely unexpected, this towering feature invites us to explore the boundaries of our knowledge about moon formation and evolution. With each step forward, we edge closer to solving this cosmic riddle, but there's still much to learn. As we ponder the origins of this extraordinary ridge, let's turn our attention next to another fascinating aspect of Saturn's moons, Phoebe's unusual composition. Phoebe's composition, a window into the solar system's past. Let's shift our focus now to one of Saturn's most intriguing moons, Phoebe. A small yet fascinating object with a composition that hints at secrets from the early days of our solar system. Unlike many of Saturn's other moons, Phoebe orbits in the opposite direction to Saturn's rotation, a characteristic known as retrograde motion. This unusual behavior sets it apart and raises questions about its origins and history. What makes Phoebe truly remarkable is its makeup. Studies conducted by NASA Cassini spacecraft revealed that this moon contains materials strikingly similar to those found in distant Kuiper belt objects, icy, rocky bodies located beyond Neptune. These findings suggest that Phoebe might not have formed alongside Saturn, but instead originated much farther out in the solar system before being captured by the planet's gravitational pull. The presence of water ice, along with organic compounds such as carbon dioxide and ammonia, provides further evidence of Phoebe's distant origins. Scientists believe these components could only have remained stable under the frigid conditions of the outer solar system. If true, this would mean Phoebe serves as a preserved relic from the solar system's infancy, offering valuable insights into the processes that shaped our cosmic neighborhood billions of years ago. But what does Phoebe's composition tell us about the dynamics of the early solar system? One possibility is that interactions between young planets and smaller bodies caused some objects to migrate inward toward the gas giants like Saturn. In this scenario, Phoebe might have been nudged into Saturn's vicinity through gravitational tugs and collisions during a chaotic period when the solar system was still forming. Understanding how such migrations occurred can help scientists piece together the larger puzzle of planetary formation and evolution. Another implication of Phoebe's unique nature lies in its potential connection to the delivery of essential building blocks for life to the inner solar system. Organic compounds carried by objects like Phoebe may have played a role in seeding Earth and other terrestrial planets with the raw materials necessary for life's emergence. By studying Phoebe, researchers gain clues about the pathways through which volatile substances traveled across vast distances within the solar system. Despite these revelations, much remains unknown about Phoebe's past. For instance, how exactly did it end up orbiting Saturn? Was it captured intact, or did it break apart during its journey? And why does its surface appear so heavily cratered compared to other moons in the Saturnian system? These open questions underscore the importance of continued exploration and observation of this enigmatic moon. In summary, Phoebe stands as a critical piece in the jigsaw puzzle of our solar system's history. Its distinctive composition links it to regions far removed from Saturn, providing tantalizing glimpses into the events that sculpted our celestial environment. As we delve deeper into the mysteries surrounding Phoebe, we inch closer to unraveling the intricate story of how our solar system came to be, and perhaps even how life itself began. With this newfound understanding, let's now explore another captivating mystery tied to Saturn's realm: the peculiarities of its magnetic field anomalies. Shifting our gaze from the distant moon Phoebe to another dazzling phenomenon in Saturn's cosmic repertoire, let's explore the mesmerizing spectacle of Saturn's auroras. Just as Earth dazzles with its northern and southern lights, Saturn too boasts its own version of these celestial light shows, but with some striking differences that make them all the more intriguing. At first glance, Saturn's auroras might appear similar to those on Earth, glowing curtains of light painting the polar regions, but a closer look reveals they are far more complex and mysterious. For one, Saturn's auroras occur at much higher altitudes above its surface compared to Earth's, stretching hundreds of kilometers into space. This immense scale makes them some of the largest auroral displays in the solar system, dwarfing even the most spectacular earthly displays. Another key difference lies in their frequency. While Earth experiences regular auroral activity driven by solar wind interactions, Saturn's auroras are less predictable and can vary dramatically depending on the planet's magnetic field dynamics. Sometimes they flare up brilliantly across vast regions of the poles, while at other times they may be faint or entirely absent. These fluctuations hint at mechanisms influencing Saturn's auroras that we have yet to fully understand. What also sets Saturn's auroras apart is their unusual behavior under certain conditions. Unlike Earth's predominantly green and pinkish hues, Saturn's auroras glow in shades of ultraviolet and infrared light, invisible to the human eye but captured beautifully by instruments like NASA's Hubble Space Telescope and Cassini orbiter. Occasionally, however, visible light auroras do occur, producing stunning blue and violet tones that rival any terrestrial display. Scientists believe Saturn's auroras arise from interactions between the planet's magnetic field and charged particles from both the solar wind and its own moons, particularly Enceladus, which spews water vapor and ions into space. Yet, despite this understanding, many questions remain unanswered. Why do Saturn's auroras sometimes pulse rhythmically, almost like a heartbeat? How does the planet's unique magnetic field configuration, nearly perfectly aligned with its rotation axis, affect these displays? And what role do Saturn's rings play in modulating the energy flows driving the auroras? These mysteries deepen when considering how Saturn's auroras interact with its upper atmosphere. Unlike Earth, where auroras primarily heat the ionosphere, Saturn's auroras seem to influence deeper atmospheric layers, potentially affecting weather patterns and even long-term climate trends on the planet. Understanding these connections could provide insights not just into Saturn itself, but also into the broader workings of magnetospheric systems throughout the solar system. As we marvel at the breathtaking beauty of Saturn's auroras, it becomes clear that there is still much to learn about the processes shaping these ethereal phenomena. By continuing to study them, scientists hope to unlock secrets about Saturn's magnetic environment and its interactions with the surrounding cosmos. Until then, Saturn's auroras remain one of the most captivating unsolved puzzles in planetary science, inviting us to wonder, and perhaps one day discover, the forces behind their dazzling dance across the heavens. Radio emissions from Saturn, a cosmic symphony of signals venturing deeper into the enigmatic world of Saturn. Let us now turn our attention to another fascinating phenomenon, its mysterious radio emissions. These natural signals, first detected by spacecraft such as Voyager and later studied in greater detail by Cassini, offer a tantalizing glimpse into the workings of Saturn's magnetic environment. Imagine the planet as a giant celestial broadcaster, emitting radio waves that can be picked up millions of miles away. But what exactly are these signals telling us, and why do they continue to baffle scientists? At their core, Saturn's radio emissions arise from processes involving its powerful magnetic field and interactions with charged particles within its magnetosphere. Known as Saturn kilometric radiation, or SKR for short, though we'll spell it out as Saturn kilometric radiation to keep things clear for text-to-speech systems, these emissions occur at frequencies ranging from tens of kilohertz to several megahertz. This range places them well within the realm of radio waves, making them detectable by specialized instruments aboard space probes. One of the most intriguing aspects of Saturn's radio emissions is their close connection to the planet's rotation rate. Unlike Earth, where the day length is relatively straightforward to measure, determining Saturn's exact rotation period has proven surprisingly challenging. The gas giant lacks solid surface features that could serve as reference points, so scientists must rely on indirect methods. Here, the radio emissions come into play, acting as a kind of natural metronome. By analyzing fluctuations in the SKR signals, researchers have attempted to deduce how fast Saturn spins on its axis. However, this method has revealed inconsistencies that deepen the mystery further. For instance, observations suggest that the frequency of Saturn's radio emissions varies over time, potentially indicating changes in the planet's apparent rotation rate. Some studies even hint at differences between the northern and southern hemispheres, raising questions about whether Saturn's rotation is truly uniform across the globe. Could there be regional variations in the way the magnetic field behaves, or might something else entirely influence the timing and intensity of these radio broadcasts? Another layer of complexity comes from the relationship between Saturn's magnetic field and its radio emissions. While we know the magnetic field plays a crucial role in generating these signals, the precise mechanisms remain unclear. Scientists believe that charged particles spiraling along magnetic field lines produce the radio waves through a process akin to synchrotron radiation. Yet, Saturn's magnetic field is unusual compared to other planets. It is almost perfectly aligned with the planet's rotation axis, unlike Earth's tilted field. This near-perfect alignment challenges traditional models of magnetospheric dynamics and raises questions about how such a configuration affects the production of radio emissions. Adding to the puzzle, Saturn's radio emissions exhibit periodic bursts and pulses that seem to follow no discernible pattern. Sometimes the signals flare up dramatically, while at other times they weaken or disappear altogether. What triggers these variations? Is it tied to solar wind activity, internal processes within Saturn, or perhaps external influences like its moons and rings? Enceladus, with its geysers spewing charged particles into space, could be one contributor, but the full picture remains elusive. As we delve deeper into the data, new mysteries emerge. For example, why do Saturn's radio emissions sometimes synchronize with auroral activity, yet at other times appear disconnected? How does the energy driving these signals transfer through the magnetosphere? And importantly, what can studying these emissions teach us about planetary magnetic fields more broadly, not just on Saturn but throughout the solar system? In many ways, Saturn's radio emissions represent a cosmic symphony, each signal a note in a grand composition written by forces we are only beginning to understand. As technology advances and future missions explore Saturn's environs, answers may begin to unfold. Until then, these cryptic broadcasts stand as yet another testament to the boundless wonders and enduring puzzles of the ringed planet. Shifting our gaze from Saturn's enigmatic radio emissions, let us now explore a captivating phenomenon tied to the planet's stunning rings, Saturn's ring shadows. These celestial silhouettes, most dramatically observed during Saturn's equinoxes, offer scientists a unique opportunity to study the intricate structures and properties of the rings in unprecedented detail. Every 14 years or so, Saturn experiences an equinox when its rings are edge onto the Sun. During this brief period, sunlight strikes the rings at an extremely low angle, casting long shadows onto the planet's surface and even across the rings themselves. These shadows become more pronounced as the equinox approaches, creating dramatic contrasts that reveal subtle features otherwise hidden in the bright glare of direct sunlight. It is during these rare events that researchers can observe phenomena such as vertical structures jutting out from the plane of the rings, providing valuable insights into their three-dimensional nature. One fascinating aspect of Saturn's ring shadows lies in how they help scientists measure the sizes and distribution of particles within the rings. When light passes through the rings, it interacts with the countless icy particles that compose them. Larger particles cast sharper shadows, while smaller ones scatter light in different directions. By analyzing the patterns and shapes of these shadows, researchers can infer the range of particle sizes present in various regions of the rings. For instance, some parts of the rings consist predominantly of tiny, micron-sized grains, while others contain larger chunks measuring several meters across. Understanding this diversity is crucial for unraveling the history and evolution of Saturn's rings. Moreover, the shadows provide clues about the overall structure of the rings. Scientists have discovered that the rings are not uniformly flat but exhibit gentle undulations and warps. These deviations from perfect planarity suggest complex gravitational interactions between the rings and nearby moons. Enceladus, Titan, and other satellites exert tidal forces that shape the rings over time, causing ripples and kinks that become visible during equinox observations. Studying these effects allows researchers to refine models of ring dynamics and better understand the delicate balance of forces maintaining their stability. Another intriguing feature revealed by Saturn's ring shadows is the presence of transient phenomena such as propellers and spokes. Propellers are small gaps carved by embedded moonlets too small to be directly imaged, yet large enough to disturb the surrounding material. As these objects orbit within the rings, they create distinctive patterns resembling airplane propellers, which cast elongated shadows detectable during equinox periods. Similarly, spokes' mysterious radial markings appearing in the B-ring are thought to result from electrostatic forces lifting fine particles above the ring plane. Observing their shadows helps scientists investigate the underlying mechanisms driving these ephemeral structures. The role of Saturn's equinoxes extends beyond mere observation. They also serve as natural laboratories for testing theoretical predictions. Models of ring behavior developed prior to equinox events can be compared against actual observations, allowing scientists to validate or revise their assumptions. For example, early theories suggested that the rings might flatten significantly during equinox due to reduced solar radiation pressure. However, subsequent measurements showed only minor changes, prompting further investigation into the factors governing ring thickness. In summary, Saturn's ring shadows represent far more than mere optical curiosities. They are vital tools for unlocking the secrets of one of the solar system's most iconic features. Through careful analysis of these shadowy projections, researchers continue to uncover new details about the composition, structure, and dynamics of Saturn's rings. With each passing equinox, we gain a deeper appreciation for the intricate dance of light and matter occurring around this magnificent planet. Moving on from the fascinating insights into Saturn's ring shadows, let us now turn our attention to another captivating mystery involving the planet's rings, the enigmatic disappearing spokes. These transient radial features appear in Saturn's B ring, creating a striking visual phenomenon that has puzzled scientists since their discovery by the Voyager spacecraft in the early 1980s. Unlike the stable structures observed in other parts of the rings, these spokes are ephemeral, appearing and vanishing over relatively short periods, sometimes lasting just minutes or hours before fading away entirely. The formation of these mysterious spokes is believed to involve a combination of electrostatic forces and orbital dynamics, though the exact mechanisms remain somewhat elusive. One prevailing theory suggests that electrostatic levitation plays a key role in their creation. Under this hypothesis, tiny ice particles within the B ring become electrically charged due to interactions with Saturn's magnetic field or exposure to ultraviolet radiation from the Sun. Once charged, these particles are lifted above the ring plane, forming delicate, spoke-like structures that align radially outward from the planet. The movement of these particles appears synchronized with the rotation of Saturn's magnetic field, further supporting the idea that electromagnetic forces are at play. Another intriguing aspect of the spokes is their connection to orbital resonance. Certain regions of the B ring may experience gravitational influences from Saturn's moons, which could amplify the effects of electrostatic levitation. For example, resonant interactions between the moon mimas and the ring material might enhance the lifting of charged particles, contributing to the formation of the spokes. Additionally, the rapid rotation of Saturn itself could influence the behavior of these structures, as they often seem to move at speeds different from the surrounding ring material. Despite these promising theories, significant gaps in our understanding of the spokes persist. Why do they appear only under specific conditions? Why do some spokes last longer than others? And why have they been less frequently observed during recent years compared to earlier missions like Voyager? Scientists continue to seek answers to these questions, hoping for new clues through advanced simulations and observations from future space missions. One particularly puzzling observation involves the relationship between the spokes and seasonal changes on Saturn. It seems that these phenomena are more common during certain times of the planet's year, possibly linked to variations in solar illumination or temperature gradients across the rings. This seasonal dependence adds another layer of complexity to the mystery, suggesting that multiple factors, electromagnetic, gravitational, and thermal, interact in ways we have yet to fully comprehend. Moreover, the study of the spokes provides valuable insights into the microphysics of Saturn's rings. By analyzing their appearance, duration, and disappearance, researchers can infer details about the properties of the ring particles, such as their size, charge distribution, and response to external forces. Such information not only enhances our understanding of the B ring, but also sheds light on the broader dynamics governing the entire ring system. In summary, the disappearing spokes represent one of Saturn's most intriguing puzzles, blending elements of electromagnetism, orbital mechanics, and planetary science. While current theories offer plausible explanations for their origin and behavior, much remains unknown about these ethereal features. As technology advances and new data becomes available, scientists hope to unravel the secrets behind these fleeting patterns, bringing us closer to deciphering the intricate workings of Saturn's magnificent rings. Shifting our focus now to another profound mystery of Saturn, let's delve into the peculiarities surrounding its magnetic field. Unlike most planets in our solar system, Saturn boasts a magnetic field that aligns almost perfectly with its rotation axis. This near-perfect alignment defies expectations and poses significant challenges to traditional dynamo theory, which attempts to explain how planetary magnetic fields are generated. In conventional dynamo theory, a planet's magnetic field arises from the motion of electrically conductive fluids, typically molten metal or plasma, within its interior. These movements create electrical currents, generating a magnetic field through processes akin to those seen in an electric generator. For this process to work effectively, it generally requires some degree of asymmetry between the rotation axis and the magnetic field axis. However, Saturn's magnetic field axis deviates by less than 1 degree from its rotation axis, making it an extraordinary outlier among the planets we've studied so far. This remarkable symmetry raises several intriguing questions. How does Saturn maintain such precise alignment? And what mechanisms could produce a magnetic field under these conditions without violating fundamental principles of physics? Scientists have proposed various hypotheses to address these conundrums, but none provide a complete explanation yet. One possibility involves unique properties within Saturn's core. Unlike Earth, whose solid iron core contributes significantly to its magnetic field generation, Saturn's core may consist primarily of compressed hydrogen and helium, possibly mixed with heavier elements. If the core lacks sufficient differentiation or if its composition differs dramatically from typical assumptions, it could influence how the dynamo operates. For instance, a more uniform distribution of materials might reduce asymmetries necessary for conventional dynamo action, leading instead to the observed alignment. Another line of inquiry explores whether external factors play a role in shaping Saturn's magnetic field. Interactions between Saturn's rapid rotation and its intense internal heat might generate complex fluid motions that counteract expected asymmetries. Alternatively, subtle influences from Saturn's moons or rings could subtly affect the internal dynamics, contributing to the unusual stability of the magnetic field. Yet another hypothesis considers the potential impact of Saturn's atmosphere and magnetosphere on its magnetic field. Strong winds and other atmospheric phenomena might interact with charged particles trapped within the magnetosphere, influencing the overall structure of the field. While still speculative, this idea suggests that external forces beyond the planet's core could help explain the anomaly. Despite these theories, many aspects of Saturn's magnetic field remain unexplained. The lack of observable tilt makes it difficult to apply standard models directly, leaving researchers searching for innovative ways to test their ideas. Advanced computer simulations and ongoing observations from spacecraft like Cassini have provided valuable insights, yet definitive answers continue to elude us. Understanding Saturn's magnetic field anomalies holds broader implications for planetary science as well. It challenges our understanding of dynamo processes across different types of planets and moons, encouraging scientists to refine existing theories or develop entirely new frameworks. By unraveling the secrets behind Saturn's magnetic quirks, we gain crucial knowledge about planetary interiors, magnetic field generation, and the diverse range of celestial bodies populating our universe. As research progresses, future missions equipped with advanced instruments will undoubtedly shed further light on this fascinating mystery. Until then, Saturn's near-perfectly aligned magnetic field remains one of the most intriguing puzzles in planetary science, inviting curiosity and inspiring exploration among scientists worldwide. Turning our attention now to another tantalizing mystery of Saturn's moons, let's explore the intriguing possibility that Dione may conceal a subsurface ocean beneath its frozen exterior. This revelation adds yet another layer of complexity to our understanding of Saturn's diverse satellite system and raises fascinating questions about the potential for habitability beyond Earth. Dione, one of Saturn's larger moons, has long been thought of as a relatively quiet celestial body composed primarily of water, ice, and rock. However, recent observations and data gathered by NASA Cassini spacecraft have hinted at something far more dynamic hidden beneath its icy surface. Scientists believe there is compelling evidence suggesting that Dione might harbor a liquid water ocean deep below its solid crust. If confirmed, this would make Dione the latest member in an elite group of icy moons, including Enceladus and Europa, that are thought to possess subsurface oceans. The primary clue pointing toward this hidden ocean comes from gravitational measurements taken during Cassini flybys. These readings revealed slight variations in Dione's rotation and orbital dynamics, indicating that the moon's interior structure might not be entirely rigid. Instead, these anomalies suggest the presence of a global or regional ocean separating Dione's icy crust from its rocky core. Such a scenario aligns with similar findings on other moons where tidal forces generated by their parent planet create enough heat to maintain liquid water beneath the surface. The significance of such a discovery cannot be overstated. Water is a fundamental ingredient for life as we know it, and the existence of a subsurface ocean on Dione opens up exciting possibilities for astrobiology. While no direct signs of biological activity have been detected, the conditions within these hidden oceans could potentially support microbial life. The interaction between water, minerals from the rocky core, and energy sources derived from tidal heating creates environments strikingly similar to those found around hydrothermal vents on Earth, places teeming with unique ecosystems despite extreme conditions. Further supporting this hypothesis are studies examining the chemical composition of Dione's surface. Spectroscopic analysis conducted by Cassini suggests the presence of hydrated materials, which could indicate past or present interactions between water and silicate rocks. Additionally, faint traces of oxygen detected in Dione's thin atmosphere point toward geological processes occurring beneath the surface, possibly linked to an active ocean system. While the evidence remains indirect, ongoing research continues to refine our understanding of Dione's internal structure. Advanced computer models simulate how tidal stresses might influence the moon's behavior, while laboratory experiments replicate the high-pressure conditions expected in its hypothesized ocean. Together, these efforts aim to uncover the mechanisms driving Dione's potential habitability and assess whether it shares characteristics with other ocean worlds like Enceladus or Europa. For scientists studying planetary science and astrobiology, Dione represents a vital piece of the puzzle in understanding the prevalence of subsurface oceans across our solar system. Its inclusion among the growing list of candidates expands our knowledge of where life might exist beyond Earth and highlights the importance of continuing exploration missions to probe deeper into these mysterious worlds. As investigations progress, future missions equipped with cutting-edge instruments will undoubtedly reveal more secrets about Dione's hidden depths. Until then, the prospect of a subsurface ocean lurking beneath its icy veneer keeps researchers intrigued and inspires further inquiry into the fascinating realm of Saturn's enigmatic moon. Shifting our gaze to another intriguing possibility within Saturn's system, let's delve into the curious case of Rhe and its potential rings. Among Saturn's many moons, Rhe stands out not only for its size but also for an unusual claim that has sparked debate among scientists: the idea that this moon might possess a faint ring system. The notion of rings around Rhe first emerged in 2008 when data collected by NASA Cassini spacecraft during a close flyby revealed unexpected readings. These measurements indicated a drop in the number of electrons detected near Rhe, suggesting the presence of material blocking their path. This observation led researchers to propose the existence of thin, faint rings orbiting the moon. However, subsequent investigations have cast doubt on this hypothesis, leaving the question unresolved. Supporters of the ring theory point to the electron density profiles observed during the Cassini encounter as key evidence. The data showed distinct gaps where fewer charged particles were detected, which some scientists interpret as being caused by solid material, likely dust or small particles, in orbit around Rhe. If true, these rings would be extraordinarily faint compared to Saturn's dazzling bands, composed mostly of tiny particles rather than large chunks of ice and rock. However, skepticism remains strong due to the lack of direct visual confirmation. Despite extensive imaging efforts by Cassini, no visible signs of rings have been captured around Rhe. In fact, follow-up studies suggest alternative explanations for the original observations. For instance, it's possible that the observed electron depletion was caused by localized phenomena such as plasma interactions or surface emissions from Rhe itself, rather than an actual ring system. Moreover, theoretical models present challenges to the feasibility of rings forming around Rhe. Unlike larger planets with stronger gravitational fields, moons like Rhe may struggle to maintain stable ring systems. Over time, gravitational influences from Saturn and other nearby bodies could disrupt any delicate structures, causing them to dissipate quickly. Additionally, Rhe's relatively low mass and weak magnetic field make it less likely to retain significant amounts of orbiting debris. Despite these doubts, the possibility of rings around Rhe continues to intrigue scientists. Understanding why or why not they exist offers valuable insights into the dynamics of smaller celestial bodies and their interactions with surrounding environments. It also highlights the importance of considering multiple interpretations when analyzing complex datasets, reminding us how much there is still to learn about even seemingly familiar objects in our solar system. In summary, while the idea of rings around Rhe captures the imagination, the current evidence remains inconclusive. Future missions equipped with more advanced instruments may one day shed light on this mystery, answering whether Rhe truly wears a crown of faint rings or if the initial observations were merely a cosmic illusion. Until then, the enigma persists, adding yet another layer of fascination to the ever-expanding catalogue of Saturn's mysteries. Moving our focus to another remarkable feature of Saturn's moons, let's explore Tethys and its colossal impact basin, Odysseus. This massive crater stretches across nearly one-third of Tethys' diameter, making it one of the most striking geological formations in the entire Saturnian system. The sheer scale of Odysseus raises intriguing questions about the size of the object that created it, and whether similar cataclysmic events have shaped other celestial bodies in this region. Odysseus measures approximately 450 kilometers in diameter, which is an extraordinary proportion relative to Tethys' overall size of just over 1,000 kilometers. Scientists estimate that the impactor responsible for carving out this immense basin must have been quite large, possibly as wide as 30 to 40 kilometers. Such a collision would have released an unfathomable amount of energy, reshaping the moon's surface and potentially altering its internal structure. Interestingly, despite the enormity of the impact, Tethys survived intact, though forever scarred by this ancient event. One fascinating aspect of studying Odysseus is understanding how such a massive impact could occur without completely destroying the moon. The answer likely lies in the composition and density of Tethys itself. Made predominantly of water ice, Tethys may have absorbed much of the impact energy through deformation rather than fragmentation. This resilience demonstrates the unique properties of icy bodies in the outer solar system and highlights the complex interplay between material strength and cosmic collisions. Beyond the specifics of Odysseus, the existence of such a colossal crater prompts speculation about the frequency and scale of similar impacts elsewhere in the Saturnian system. Other moons, like Mimas with its iconic Herschel crater, show evidence of similarly dramatic encounters. However, each case presents distinct characteristics depending on factors such as the moon's size, composition, and location within Saturn's gravitational influence. By comparing these craters, researchers gain valuable insights into the dynamics of the early solar system, including the distribution and movement of objects during its formation. Another intriguing element of Odysseus is its current appearance. Over billions of years, the crater has undergone significant modification due to processes like viscous relaxation, where the icy crust slowly flows under its own weight, smoothing out some of the original features. As a result, the rim of Odysseus appears less sharp today compared to when it was first formed. Studying these changes helps scientists understand not only the history of Tethys, but also the long-term evolution of icy worlds throughout the solar system. Furthermore, the presence of Odysseus invites consideration of the broader implications for planetary defense here on Earth. While our planet benefits from a protective atmosphere that burns up smaller asteroids before they reach the surface, larger impacts can still pose serious threats. Observing the scars left behind on distant moons like Tethys provides context for the potential consequences of asteroid strikes closer to home and underscores the importance of ongoing efforts to monitor near-Earth objects. In summary, Tethys' enormous impact basin, Odysseus, serves as both a testament to the violent history of the solar system and a window into the peculiarities of icy moon geology. Its study enriches our understanding of past collisions and their effects on celestial bodies, while also sparking curiosity about comparable phenomena elsewhere in the Saturnian system. As we continue to unravel the mysteries surrounding Tethys and its companions, each new discovery brings us closer to comprehending the intricate dance of forces that govern our universe. Shifting our gaze from the battered surface of Tethys, let's now journey to Saturn's largest moon, Titan, where a truly alien weather system unfolds. On this distant world, rain doesn't fall as water, but instead as liquid methane, a hydrocarbon compound that behaves like water in Titan's frigid temperatures. This unique phenomenon has captivated scientists for decades, offering a glimpse into processes eerily similar yet fundamentally different from those on Earth. The Huygens probe, which landed on Titan in 2005, provided invaluable data about its atmosphere and surface. It revealed a landscape carved by flowing liquids, with river channels, lakes, and seas composed primarily of methane and ethane. These discoveries were further bolstered by observations from the Cassini orbiter, which spent 13 years studying the Saturnian system. Together, these missions uncovered the intricate dynamics of Titan's methane-based weather cycle. On Earth, the water cycle involves evaporation, condensation, cloud formation, and precipitation. On Titan, an analogous process occurs with methane. Methane evaporates from its surface lakes and seas, rises into the atmosphere, cools, and condenses into clouds. Eventually, it falls back down as rain, replenishing the bodies of liquid below. However, unlike Earth's relatively stable climate, Titan's weather patterns are influenced by extreme seasonal variations due to its long orbital period around Saturn. A single year on Titan lasts nearly 30 Earth years, meaning each season stretches for over 7 years. During these prolonged periods, the location and intensity of methane rain can shift dramatically, altering the Moon's surface features over time. One of the most intriguing aspects of studying Titan's methane cycle is understanding how it compares to Earth's water cycle. Both systems involve complex interactions between the surface, atmosphere, and subsurface reservoirs. Yet, while Earth's water cycle supports life as we know it, Titan's methane cycle operates in conditions far too cold for familiar biology. Nevertheless, some researchers speculate that exotic forms of life might exist within Titan's hydrocarbon-rich environment, adapted to thrive in ways unimaginable on our planet. Observations suggest that Titan's weather is not static but undergoes significant changes over millennia. For instance, radar images taken by Cassini show evidence of dried lake beds near the equator, indicating that methane rainfall once occurred in regions where it is scarce today. Scientists hypothesize that shifts in Titan's axial tilt or orbital parameters could drive these climatic transformations, much like Milankovitch cycles influence Earth's ice ages. Unraveling these mysteries requires a deeper understanding of the forces shaping Titan's atmosphere and surface. Moreover, the study of Titan's methane cycle offers insights into the broader question of planetary habitability. By comparing Titan's hydrocarbon-based processes to Earth's water-driven ones, scientists gain clues about the conditions necessary for sustaining dynamic climates across diverse celestial environments. This comparative approach highlights the remarkable adaptability of natural systems and underscores the importance of exploring worlds beyond our own. As fascinating as Titan's methane rain may be, many questions remain unanswered. How exactly does the Moon maintain such an active cycle given its distance from the Sun? What role do internal heat sources play in driving evaporation and replenishment? And perhaps most tantalizingly, what secrets lie hidden beneath the opaque haze shrouding Titan's surface? Each new observation brings us closer to answering these enigmas, revealing a moon whose alien beauty rivals the complexity of our home planet. Venturing deep into the heart of Saturn, we encounter one of its most perplexing enigmas, the nature of its core. For decades, scientists have debated whether Saturn's core is a solid mass, a swirling liquid expanse, or perhaps something entirely beyond our current understanding. This mystery lies at the very foundation of how we interpret not just Saturn itself, but also the processes that govern planetary formation across the universe. Current theories suggest that Saturn's core might consist of a dense amalgamation of rock and ice, compressed under unimaginable pressures into a state unlike anything found on Earth. However, recent studies challenge this notion, proposing that instead of being solid, the core could be more akin to a supercritical fluid, a phase where distinctions between liquid and gas blur due to extreme conditions. If true, this would redefine our comprehension of what constitutes a planetary core and raise profound questions about how such structures form and evolve over billions of years. Understanding Saturn's core composition holds critical implications for planetary science as a whole. Traditional models of planetary formation rely heavily on the assumption that gas giants like Saturn and Jupiter begin with a rocky seed, a solid core around which vast quantities of hydrogen and helium accumulate. Yet, if Saturn's core defies this expectation, it forces us to reconsider these long-standing paradigms. Could gas giants arise without a solid core, or do they undergo transformations over time, altering their internal architecture in ways we have yet to fully grasp? One compelling theory posits that Saturn's core may not even exist as a distinct entity, but rather as a gradual transition zone where heavier elements blend seamlessly with lighter ones. In this scenario, there would be no clear boundary separating the core from the surrounding layers of metallic hydrogen and molecular gas. Such a structure would imply an entirely different evolutionary path for Saturn compared to other planets in our solar system. The search for answers continues through advanced simulations and observations, though direct evidence remains elusive. Instruments aboard missions like Cassini provided invaluable data about Saturn's gravitational field and density distribution, offering tantalizing hints about its inner workings. Still, much remains unknown, leaving researchers to piece together fragments of information like detectives solving a cosmic puzzle. Exploring Saturn's core challenges us to rethink fundamental assumptions about planet formation and evolution. Each new discovery brings us closer to unraveling the secrets buried within this distant world, while simultaneously highlighting the complexity and diversity of celestial bodies throughout the cosmos. As we delve deeper into this mystery, one thing becomes increasingly clear. Saturn's core is far more than just the center of a giant gas ball. It is a window into the very processes that shape the universe itself. This exploration invites us to consider broader implications about the origins of planets everywhere, reminding us that even after centuries of study, the mysteries of space continue to inspire awe and curiosity. With every step forward, we edge closer to unlocking the hidden truths beneath Saturn's majestic exterior. Moving our focus outward from Saturn's core, let's journey to one of its most intriguing moons, Mimas. Often nicknamed the Death Star moon due to its striking resemblance to the fictional space station, Mimas plays a pivotal role in shaping Saturn's rings through gravitational interactions. These interactions create fascinating patterns and gaps within the rings, offering us a glimpse into the intricate dance of celestial mechanics. Mimas exerts its influence primarily through orbital resonances, a phenomenon where two orbiting bodies affect each other's motion due to periodic gravitational pulls. In the case of Saturn's rings, Mimas' gravitational tugs generate specific effects that leave their mark on the delicate structure of the ring system. One of the most notable outcomes of this interaction is the formation of gaps areas within the rings where particles are either swept away or prevented from accumulating. The best-known example of Mimas' handiwork is the Enceladus gap, located within Saturn's ring. This gap arises because Mimas' orbital resonance clears out particles at certain distances from Saturn, creating a void that stands as a testament to the moon's gravitational reach. However, the story doesn't end there. Beyond mere gaps, Mimas also contributes to the creation of wave-like patterns across the rings. These density waves ripple outward like water disturbed by a stone, adding layers of complexity to the already mesmerizing sight of Saturn's rings. But why does this happen? The answer lies in the mathematics of orbital dynamics. When Mimas completes a specific number of orbits relative to the ring particles, it creates a repeating pattern of gravitational forces. This repetition amplifies over time, sculpting the rings into the shapes we observe today. Scientists study these patterns not only to understand the behavior of Saturn's rings, but also to refine models of planetary ring systems throughout the universe. Interestingly, Mimas isn't alone in influencing Saturn's rings. However, its unique position and mass make its effects particularly pronounced. By examining these gravitational interactions, researchers gain insights into how small moons can shape massive structures, revealing the delicate balance between chaos and order in the cosmos. As we continue to explore Saturn's ring system, Mimas serves as both an architect and a guide, pointing us toward deeper truths about the workings of our solar system. This interplay between Mimas and Saturn's rings highlights the interconnectedness of celestial objects, reminding us that even the smallest players in the grand cosmic theater can wield significant influence. Understanding these processes enriches our knowledge of planetary science and underscores the beauty of nature's intricate designs. Let's shift our focus now to one of the most fascinating orbital ballets in the Saturnian system, the cosmic dance between Epimetheus and Janus. These two moons, roughly similar in size, share an extraordinary relationship that defies conventional expectations of celestial mechanics. Instead of following stable, independent orbits, they engage in a remarkable exchange where they swap positions every 4 years. This phenomenon is not just a quirk of nature but a testament to the intricate balance governing gravitational forces in space. To understand this unique behavior, we must first grasp the basics of their shared orbit. Both Epimetheus and Janus occupy nearly identical paths around Saturn, with only a slight difference in distance from the planet. This proximity creates a situation where their mutual gravitational pull disrupts what would otherwise be straightforward trajectories. As they approach each other during their orbits, the gravitational tugging becomes significant enough to alter their speed slightly. The result, a periodic reversal of roles as the inner moon slows down and moves outward, while the outer moon accelerates and shifts inward. This swapping process happens seamlessly over several months, culminating in a dramatic role reversal approximately every 4 Earth years. Imagine two dancers performing a perfectly synchronized routine, exchanging places without missing a beat. In this case, the dancers are celestial bodies governed by the laws of physics rather than choreography, yet the outcome is no less mesmerizing. Scientists have dubbed this interaction a horseshoe orbit, referring to the shape traced by these moons as they alternately lead and follow one another along their orbital path. What makes this dynamic so captivating is its rarity in the universe. Most moons maintain fixed orbits, undisturbed by neighboring companions. However, Epimetheus and Janus defy this norm, showcasing how even small-scale interactions can produce large-scale effects. Their co-orbital dance provides valuable insights into the complexities of gravitational systems, helping researchers refine models used to predict similar phenomena elsewhere in the cosmos. Moreover, this celestial performance highlights the delicate equilibrium at play within planetary systems. While the gravitational interplay might seem chaotic at first glance, it adheres strictly to mathematical principles. Studying such interactions allows scientists to better comprehend the formation and evolution of moons, rings, and entire planetary systems. It also underscores the importance of considering subtle influences when modeling astronomical events, reminding us that even minor players like Epimetheus and Janus contribute significantly to the grand tapestry of the solar system. As we marvel at this balancing act, it's worth reflecting on the broader implications. Could there be other examples of co-orbiting pairs beyond Saturn? Or might this arrangement exist in exoplanetary systems waiting to be discovered? Each observation brings us closer to unraveling the mysteries of orbital dynamics, further fueling our curiosity about the universe. Through the lens of Epimetheus and Janus, we glimpse not only the elegance of nature's design, but also the endless possibilities hidden within the depths of space. Shifting our gaze now to another fascinating celestial interaction, let's explore the pivotal role Prometheus plays in sculpting Saturn's iconic F-ring. This tiny moon, measuring just over 80 kilometers across, might seem insignificant compared to its gargantuan parent planet. However, Prometheus wields an outsized influence on the outermost main ring of Saturn, creating intricate patterns that captivate scientists and stargazers alike. Prometheus orbits close to the F-ring, maintaining a delicate gravitational relationship with it. As the moon moves along its elliptical path, it periodically approaches the inner edge of the F-ring, where its gravitational pull tugs at the icy particles within. This interaction doesn't merely nudge the particles slightly. Instead, it generates dramatic kinks and braids that ripple through the ring system. Imagine a potter shaping clay on a wheel. Prometheus acts as the cosmic artisan, molding and reshaping the F-ring into complex, ever-changing forms. The process begins when Prometheus ventures closest to the F-ring during its orbit, a point known as periapsis. At this juncture, the moon's gravity pulls on the nearby ring material, causing sections of the F-ring to bunch up or stretch out. These distortions are far from random. They form specific patterns resembling twists and knots, earning them their nickname, braids. The term aptly describes how these structures appear to weave together like strands of hair, although they're actually composed of countless microscopic ice particles. What makes this phenomenon even more intriguing is its dynamic nature. Unlike static features carved into stone, the kinks and braids in the F-ring are transient, constantly evolving due to Prometheus' ongoing interactions. Over time, these patterns shift and reconfigure as Prometheus completes its orbit and repeats the cycle. Scientists studying these changes gain valuable insights into the mechanics of gravitational forces operating at small scales within planetary rings. Moreover, this interplay between Prometheus and the F-ring provides clues about the larger processes shaping Saturn's entire ring system. Rings aren't static disks, but rather dynamic environments governed by countless tiny collisions and gravitational nudges. By observing how Prometheus influences the F-ring, researchers can extrapolate broader principles applicable to other parts of Saturn's rings and potentially even to ring systems around other planets. Another remarkable aspect of this interaction is the way Prometheus leaves behind visible trails in its wake. When the Moon retreats after reaching periapsis, it carves temporary gaps and wakes in the F-ring, which dissipate gradually as the disturbed particles settle back into place. These fleeting imprints serve as a testament to the Moon's power despite its diminutive size, reinforcing the idea that even minor components of a system can have profound effects. As we delve deeper into understanding Prometheus' role in sculpting the F-ring, one cannot help but marvel at the intricate dance of forces at play. It exemplifies how seemingly simple gravitational interactions can give rise to breathtaking complexity, offering a glimpse into the universe's inherent artistry. Furthermore, this spectacle underscores the importance of studying smaller bodies within planetary systems, reminding us that every piece contributes uniquely to the grand cosmic puzzle. With each observation, we come closer to unraveling the secrets of Saturn's rings and appreciating the elegance of nature's design. Moving our focus from the sculpting prowess of Prometheus to a broader canvas, let us now examine Saturn's mesmerizing color variations. These shifting hues paint the planet's cloud tops in a kaleidoscope of colors, offering a visual spectacle that captivates astronomers and space enthusiasts alike. Unlike Earth's relatively uniform blue skies, Saturn displays a vibrant palette ranging from soft creams and yellows to deep reds and browns, with occasional hints of green or blue. The origin of these striking variations remains one of Saturn's enduring mysteries. Scientists attribute them primarily to two factors: seasonal shifts and chemical reactions occurring within the planet's atmosphere. As Saturn completes its lengthy orbit around the Sun, taking nearly 30 Earth years to do so, it experiences profound seasonal changes. During each season, different regions of the planet receive varying amounts of sunlight, influencing atmospheric dynamics and potentially altering the composition of clouds at various altitudes. Chemical processes also play a significant role in shaping Saturn's colorful appearance. The planet's upper atmosphere contains compounds such as ammonia ice, ammonium hydrosulfide, and water ice, which interact under specific conditions to produce distinct colors. For instance, exposure to ultraviolet radiation from the Sun can trigger photochemical reactions that generate complex hydrocarbons, contributing to the rich reddish-brown tones observed on Saturn. Additionally, trace elements like phosphine and methane may undergo transformations driven by temperature fluctuations or interactions with other molecules, further diversifying the color spectrum. Interestingly, some areas of Saturn exhibit more pronounced color contrasts than others. The northern hemisphere, particularly during its summer solstice, showcases vibrant blues due to increased scattering of sunlight by smaller particles high in the atmosphere. Conversely, the southern hemisphere often appears darker and more muted during its winter phase, reflecting reduced solar activity and possibly thicker cloud layers obscuring deeper levels of the atmosphere. These observations raise intriguing questions about the underlying mechanisms driving Saturn's chromatic diversity. Are these variations purely seasonal, or could they result from longer-term trends linked to internal heat sources or external influences? Could localized storms or weather patterns temporarily enhance certain colors while suppressing others? Furthermore, what role might Saturn's magnetic field play in modulating atmospheric chemistry and thus affecting the overall hue? Speculation abounds regarding the interplay between these factors. Some researchers propose that episodic upwelling of material from deeper within Saturn could introduce fresh compounds into the upper atmosphere, sparking new chemical reactions and generating sudden bursts of color. Others suggest that interactions between Saturn's rings and its atmosphere might contribute subtle yet detectable effects, though evidence for this remains speculative. Understanding Saturn's color variations requires integrating knowledge across multiple disciplines, including meteorology, chemistry, and astrophysics. By studying how these hues evolve over time, scientists hope to unlock secrets about Saturn's atmospheric structure, circulation patterns, and energy balance. Such insights not only deepen our appreciation of this majestic gas giant, but also inform broader investigations into planetary atmospheres throughout the universe. In pondering Saturn's ever-changing tapestry of colors, we are reminded of the intricate web of forces shaping worlds far beyond our own. Each shade tells a story, each variation offers a clue, inviting us to continue exploring the enigmatic beauty of this distant planet. Shifting our gaze from Saturn's colorful cloud tops to one of its most peculiar moons, let us now explore the fascinating case of Pan, a tiny satellite nestled within the intrigue gap of Saturn's rings. This diminutive moon, measuring only about 20 kilometers across, might seem insignificant compared to larger celestial bodies, but it boasts a unique feature that has captivated scientists and observers alike: its distinctive winged appearance. Pan's unusual shape resembles a flying saucer or a walnut split open, with two prominent ridges extending along its equator. These features have earned them the nickname wings, creating an image that is both alien and mesmerizing. The origins of these structures remain a topic of intense scientific interest, with accretion processes being the leading explanation for their formation. Accretion refers to the gradual accumulation of material under the influence of gravity. In Pan's case, its position within the intrigue gap places it in close proximity to particles from Saturn's rings. As the Moon orbits Saturn, it gravitationally attracts ring material, causing it to gather around its equatorial region. Over time, this process forms the characteristic ridges we see today. Scientists believe that the wings are composed primarily of fine icy particles swept up by Pan during its journey through the gap. This phenomenon highlights the dynamic relationship between Saturn's moons and its rings. While many moons influence the structure of the rings through gravitational interactions, Pan represents a rare example where the reverse also occurs. The rings actively contribute to shaping the moon itself. This interplay underscores the intricate balance governing the Saturnian system and reveals how even the smallest objects can participate in grand cosmic processes. Further supporting this theory, observations made by NASA Cassini spacecraft provided detailed images of Pan's surface, showing evidence of recent accretion events. These findings suggest that the wings continue to grow slowly as Pan sweeps through the intrigue gap, collecting additional material over time. Such ongoing activity implies that the moon's appearance may not be static but rather evolving in response to its environment. However, questions still linger regarding the exact mechanisms driving this process. For instance, why does Pan accumulate material predominantly along its equator? One hypothesis points to centrifugal forces generated by the moon's rapid rotation, which could flatten any newly acquired debris into an equatorial disk. Another possibility involves the specific dynamics of particle capture within the intrigue gap, where certain trajectories favor deposition near the equatorial plane. Exploring these mysteries deepens our understanding of planetary systems and their complex interactions. By studying phenomena like Pan's winged appearance, researchers gain valuable insights into accretion processes and the conditions necessary for such structures to form. These discoveries resonate beyond Saturn, offering lessons applicable to other celestial environments where similar processes occur. As we marvel at Pan's curious shape, we are reminded once again of the wonders hidden within Saturn's realm. Each discovery brings us closer to unraveling the secrets of this distant world, inviting us to continue probing its depths and uncovering the marvels concealed within its rings and moons. Moving our focus from the peculiarities of Pan to the broader canvas of Saturn itself, let us delve into the planet's dramatic seasonal changes. Spanning over 29 Earth years, one full orbit around the Sun allows Saturn to experience 4 distinct seasons, each bringing its own set of transformations and atmospheric phenomena. These shifts offer a fascinating glimpse into the dynamics of this distant world, revealing how even planets far from the Sun undergo cycles reminiscent of those on Earth. Saturn's axial tilt, similar to Earth's, plays a crucial role in driving these seasonal variations. As different hemispheres receive varying amounts of sunlight throughout the year, the planet's atmosphere responds with noticeable alterations in weather patterns. One of the most striking manifestations of these changes is the evolution of storms across Saturn's surface. During certain seasons, massive storm systems emerge, some spanning thousands of kilometers, painting the planet's face with swirling clouds and violent winds. A prime example of this phenomenon occurred in 2010 when a colossal storm erupted in Saturn's northern hemisphere. Known as the Great White Spot, this rare event unfolded during the planet's spring season, showcasing powerful lightning flashes and intense wind speeds exceeding 500 kilometers per hour. Observations revealed that such storms are not merely random occurrences, but rather tied to specific times within Saturn's seasonal cycle, suggesting a deeper connection between solar radiation and atmospheric activity. Beyond storm formation, polar vortex behavior also exhibits intriguing seasonal fluctuations. At Saturn's poles, vortices form due to temperature gradients and rotational forces, creating stable structures that persist for extended periods. However, as sunlight reaches the poles during their respective summers, significant changes occur. For instance, the hexagonal jet stream encircling the North Pole shows increased activity under direct sunlight, with heightened turbulence and shifting boundaries. Meanwhile, the South Pole experiences cooling effects as it transitions into winter, leading to contrasting atmospheric conditions between the two hemispheres. These seasonal transformations highlight the complexity of Saturn's atmosphere, where multiple factors interact to produce ever-changing landscapes. Temperature variations, wind patterns, and chemical reactions all contribute to the planet's dynamic environment, offering researchers invaluable insights into planetary meteorology. By studying these processes, scientists gain a better understanding of not only Saturn, but also other gas giants throughout the universe. Moreover, the study of Saturn's seasons extends beyond mere observation of weather events. It provides clues about the planet's internal structure and energy distribution, shedding light on how heat escapes from its core and influences surface phenomena. This interplay between internal and external forces creates a delicate balance that shapes Saturn's appearance and behavior over time. As we reflect on these seasonal marvels, we are reminded once again of the intricate workings of our solar system. Each discovery brings us closer to comprehending the forces that govern distant worlds, inspiring further exploration and deepening our appreciation for the wonders of space. Shifting our focus to one of Saturn's most awe-inspiring phenomena, let's explore the enigma of the Great White Spot. This colossal storm system, which periodically erupts on the planet's surface, serves as a fitting conclusion to our list of unexplained mysteries. Unlike Earth storms, which are relatively small and short-lived, the Great White Spot is an extraordinary event that unfolds on a truly planetary scale. The Great White Spot typically appears once every Saturnian year, which equals about 29 Earth years. However, its occurrence is not strictly regular, making it even more intriguing for scientists. Records indicate that these massive storms have been observed 6 times since 1876, with each instance bringing new surprises and insights into Saturn's atmospheric dynamics. The most recent outbreak happened in 2010, capturing the attention of astronomers worldwide as it unfolded across the northern hemisphere during Saturn's spring season. What makes the Great White Spot so remarkable is its sheer size and intensity. Spanning thousands of kilometers, this storm can grow large enough to engulf entire continents if placed on Earth. Observations reveal towering clouds reaching high into Saturn's atmosphere, accompanied by intense lightning flashes that illuminate the surrounding regions. Wind speeds within the storm can exceed 500 kilometers per hour, creating a chaotic dance of swirling gases and violent turbulence. One of the most fascinating aspects of the Great White Spot is its connection to Saturn's seasonal cycle. These storms tend to emerge during specific times when increased solar radiation interacts with the planet's atmosphere, triggering complex chemical reactions and thermal gradients. Scientists believe that heat trapped beneath Saturn's cloud layers plays a critical role in fueling these eruptions. As temperatures rise due to seasonal variations, the accumulated energy bursts forth in spectacular fashion, giving birth to the Great White Spot. Despite advances in technology and observation techniques, many questions remain unanswered regarding this phenomenon. How exactly does the storm form? What mechanisms govern its timing and duration? Why does it exhibit such immense power compared to other storms in the solar system? These mysteries continue to challenge researchers, pushing them to refine models and gather more data in hopes of unraveling the secrets behind this celestial spectacle. In addition to their scientific significance, the Great White Spots hold a certain poetic allure. They remind us of nature's grandeur and the untamed forces at work in distant worlds. Each eruption tells a story of cosmic interplay between sunlight, heat, and atmospheric conditions, painting a vivid picture of Saturn's dynamic personality. As we conclude our journey through 25 unexplained mysteries, the Great White Spot stands as a testament to the wonders still waiting to be discovered in our solar system. To wrap up our journey through the 25 unexplained mysteries of Saturn, it's clear that this magnificent planet remains one of the most intriguing and enigmatic objects in our solar system. From the mesmerizing hexagon at its north pole to the colossal Great White Spot, each mystery adds another layer to Saturn's cosmic puzzle. These phenomena challenge our understanding of planetary science and remind us how much there is still to learn about the universe we inhabit. Throughout this exploration, we've uncovered a wide range of fascinating questions. Why does Saturn produce more heat than expected for its age? What drives the chaotic rotation of Hyperion or the formation of Iapetus' towering equatorial ridge? How do Titan's methane rain cycles compare to Earth's water cycle? And what secrets might Enceladus geysers hold regarding potential life beyond our planet? Each mystery not only deepens our curiosity but also pushes the boundaries of scientific discovery. Saturn's rings alone present an entire realm of unanswered queries. Are they as ancient as the planet itself, or are they relatively young features shaped by collisions and gravitational forces over time? And what about those transient spokes that appear and disappear without explanation? Every observation brings new insights while simultaneously raising fresh questions, highlighting just how dynamic and ever-changing Saturn truly is. The sheer variety of these mysteries makes Saturn a treasure trove for scientists and space enthusiasts alike. Its moons, from Titan with its thick atmosphere to Phoebe with its Kuiper belt origins, offer diverse environments that mirror different chapters in the history of the solar system. Even seemingly minor details like Pan's distinctive wings or Prometheus' role in sculpting the F-ring contribute to the larger story of this complex planetary system. As we conclude this list, remember that these 25 mysteries represent only the beginning of what Saturn has to teach us. With future missions planned and technology continuing to advance, who knows what discoveries await around the next corner? Whether you're captivated by the auroras dancing across Saturn's poles or intrigued by Dione's possible subsurface ocean, there's something here for everyone to marvel at. So tell us, what was your favorite mystery from today's video? Was it the haunting beauty of the hexagon, the mind-boggling power of the Great White Spot, or perhaps the alien-like landscape of Titan? Let us know in the comments below. If you enjoyed diving into these celestial wonders, don't forget to hit that subscribe button and turn on notifications so you never miss out on our latest space-related content. There's always more to explore, and together we can continue uncovering the secrets of the cosmos. Thank you for joining me on this incredible journey through Saturn's mysteries. It's been a pleasure sharing them with you.